Hello guys, this is Manjunath. Today I am going to show you how to do heat load calculation by using E20 sheet. This is the E20 sheet. This is the building layout, school building layout for Bangalore location. The fall ceiling height is equal to 10 feet. Median weight building equal to 80 lb per square feet. Today I will show you how to do heat load calculation for the office room G06. The length of this room is 19.73 feet. You can take 20 feet. And width of the room is 15.71 feet. You can take 16 feet approximately. And area of the glass window is 5.9 by 4 feet. You can take 6 by 4 feet. Here our window is exposed to sunlight in the direction of north. This is the north, this is the south, this is the east, and this is the west. Okay. Guys, let's we calculate. This is the heat load calculation E20 sheet. Project I mentioned school building. Area is office G06. Room size we have to put here. Length is 20 feet, width is 16 feet. So area you will get 320 square feet. And height is fall ceiling height is 10 feet and volume is 3200 cubic feet. Now I will show you how to take latitude, altitude and daily range values from design data book. This is the outside design condition for Indian cities. So our location is Bangalore. The latitude for Bangalore is 12.6 and daily range for Bangalore is 12 and altitude is 921 feet. And for school building I will take 93.2 67.3. Here they mention cooling dB and MCWB. So I will take for school building 93.2 is a dry bulb temperature and wet bulb temperature is 67.3. So these values we will put in E20 sheet. Latitude I put 12.6, altitude I put 921 and daily range is 22 degrees. Here outside air from design data book it is 93.2 dry bulb temperature and wet bulb is 67.3. With the help of dry bulb and wet bulb using psychometric chart or psychometric calculator, we will get the value 27% has a relative humidity and 64 is a humidity ratio. Now room, inside the room. For inside the room we have to keep dry bulb as a constant 75 and relative humidity is 50. So with the help of these two values we will get 63 as a wet bulb and humidity ratio is 65 with the help of psychrometric chart. And outside in inside room difference, we will get this value. Here 18.2, here 4.3, here minus 23, here minus 12. Now I will do solar gain to glass. Our window is exposed to sunlight in the north direction, so north, and area of the window is 6 by 4, it is 24 square feet. Now I will show how we get this value solar gain 28 from design data book. This is the solar heat gain through ordinary glass. So our 1 second. So our latitude is 12.6 for Bangalore. So here 0 is there, 10 is there, and 12 is not there. So I will go for higher. I will go with higher value, that is 20 north latitude. Okay. In this sheet, we have to consider the maximum temperature in the month July and May. Okay. So our window is exposed to sun in the north direction. So in the north direction, we have to take higher value in the north direction. See, north, the highest value is 28. So I will take solar gain to ordinary glass is 28. Suppose if our window is exposed to sunlight in the east direction, we have to take east. In the east, highest value is 163. We have to take 163. Okay. So north, what is exposed to sun? So north highest value is 28. So we will take 28 as a solar heat gain to ordinary glass. See here for north, area 24 square feet, solar gain from design data books it is 28. Solar factor is constant, that is 0.78. So multiply by these three values, you will get 524.16 BTU per hour. So solar heat gain two glass is done. Next is outside air. Outside air is our area, room area is, office room area is 320 square feet, and for office you assume 3 people are sitting in the office. So I put 3 people. Now I will show how to take these values, square feet and people, CFM per square feet and CFM per person from the design data book. This is the minimum ventilation rates in breathing zone. So our area is office. Okay. Here CFM per person is 5. So 5 is there. And CFM per feet square is 0.06. So we have to take these two values. Okay. If suppose any other area is there, for example reception area, take this 5 CFM per person and CFM per feet square is 0.06, like that. Okay. See here, CFM per square feet is 0.06 from design data book and CFM per person is 5. If we multiply these values, we will get this one. So total CFM is 34.2 CFM. Okay. Now we will do transmission gain, do walls and roof. Okay, our wall is exposed to north direction, so north area. The length of the wall is 20 feet. So 20 into, we have to multiply by 2 height. 2 height is 13 feet, means 10 feet fall ceiling height. We have to take extra 3 feet. So 13 feet, 20 into 13, which come 260 feet minus glass area we already calculated, it came 24 square feet. So if you subtracting this, so we will get 236 square feet. Okay. Now I will show how to take equivalent temperature difference value from design data book. This is the equivalent temperature difference. So our wall is exposed to north, here north, and our weight of the wall is 80 lb per square feet. But here 80 is not there. So what I will do, I will take the highest value from 60 and 100. If I divide it by these two, I will get the value for the building weight 80 lb per square feet. Okay. For 60, the highest value is 12. Below that, we have to take the value below only, same area, same column. Below that 8 for 100. Okay, 12 plus 8 equal to 10. Sorry, 12 plus 8 equal to 20 divided by 2, 10. Okay, so for the weight of the 80 lb per square feet, our equivalent temperature difference I will get 10. Okay, suppose if our weight of the wall is 100 lb per square feet, so in this 100 we will take highest value. Highest value is 8. I will take directly 8. Okay, here 100 is not there, 8 is there, but here 80, sorry, but here 80 is not there. For that reason I took average value. So 12 plus 8, 20 divided by 2, 10. 10 is the equivalent temperature difference. For this equivalent temperature difference 10, we have to add correction factors. Okay, I will tell you. See, our temperature difference is 1 second, guys. Okay, our temperature difference is 18.2 outside minus inside, but here 18.2 is not there. So we will go for higher value, that is 20, and daily range for Bangkok is 22. If we intersect both these 20 and daily range 22, we will get correction factor is 4. Okay, so 10 plus 4, so I will get 14. Okay guys, this I will insert in E20 sheet. See, ETD, equivalent temperature difference, I added correction factor also, 10 plus 4, 14. Now I will tell you how I will get the U value, how to take U value. Actually, you will get U value from the civil department. Otherwise, we have to take from design book. So this is the U values. For external walls, the U value is 0.089. Okay. The U value is 0.089. Okay. So if we multiply all these values, you will get 294.056. Okay guys. Now This done. Now we will do infiltration. So you will get automatically this value here 3200 cubic feet, this constant, and this air change per hour I will show. We have only this the air change per hour's value. We have only one wall exposed to sunlight, so we have to take 0.25 value. If two wall is exposed to sunlight, we have to take 0.5. But in our case, only one wall is exposed to sunlight. In our case, only one wall is exposed to sunlight, so you will take 0.25. Okay, this is a 0.25. So multiply by this, you will get 13.33. Okay, so if you add both CFM and infiltration, if you subtract outside air and infiltration, you will get net outside air 20, that is 20.8667. So net outside air is 20.8667. 34.2 minus 13.33. You will get this net outside air, guys. Okay. Now we will do for transmission gain from others. Okay. All classes it will come automatically 24 feet. Temperature difference is here 18.2. Now I will show the U value. U value for the all classes. I will show later, guys. Okay. And for non-AC partition glass, we don't have non-AC partition glass, leave it as it is. Now non-AC partition. Now we do for non-AC partition and non-AC flow. Okay. This is our building plan. So this area is already be calculated. So here next to this room is a AC room. Non-AC, this area is non-AC and this area is non-AC. So we have to calculate the value for the non-AC partition, area for the non-AC partition. Okay. First here width is 16 feet. 16 into 13. We have to multiply by 2 height, that is 13 feet. So 16 into 13 you will get 208 plus 20 into 13 you will get 260. So adding these two we will get the value for non-AC partition 468. Okay, because this area is also not a non-AC, this area also non-AC. Here non-AC partition, the 468 square feet came area, and this non-AC flow I will get here same 320, because our location is in ground floor below that non-AC. So for that reason I will take non-AC flow as a 320. And temperature difference, our total temperature difference is 18.2, and here we have to subtract 18.2 minus 5. It is a standard sky. Okay, if we subtract 18.2 minus 5 you will get 13.2, 13.2, 13.2. Suppose you will get 20. Suppose if it is outside temperature 20, so you will get 15, 15, 15, like that. And now I will show how to take the U values. This is typical fenestration characteristics. Here our glass is fixed frame and made up of material aluminum. So U value is 1.13. Okay. For our glasses, we put U value is 1.13. You will get this area. We don't have a non-AC partition glass. For non-AC partition, U value is 0.548. You will get this value. And for non-AC flow, you will get 0.36. So multiply by this, you will get these values. Actually, you will get U value from the civil department. If not, you can use this value. It is a design data book. From design data book I took, guys. Okay. Now you will do infiltration and outside air. So you no need to change anything. It will come automatically. I will show you. Infiltration, it is 13.33. So 13.33. Temperature difference is 18.2. And this is CF is conversion factor. Means converting CFM into BTU. It is constant, no need to change anything. 1.08 is bypassed outside air 20.86 20.8667 and temperature difference is 18.2 and bypass factor is 0.1. It is constant. This converting factor this conversion factor is also constant 1.08. Okay, so you will get these values. Now, so infiltration and outside air is done. Now I will do internal gate, insensible gate. Here people, light, appliance and miscellaneous play. Okay. Here people in office room we have three peoples and this is sensible heat. I will show you from design book. See heat gain from people. We are doing heat load calculation for the office. So sensible heat is 245 B2 per hour and latent heat is 155 B2 per hour. The sensible heat is 245. Okay. So you will get people total, you will get 735. Now I will calculate for lights. This is lighting power densities. Our office is enclosed, so you have to take this value 1.1 watt per feet square, and we have to multiply by our office total area. So 1.1 into 320, we have to multiply 1.1 into 320, so you will get 352. See lights 1.1 into 1.1 into 320, I will get 352 watts, and this is constant ballistic factor 1.25. This conversion factor is also constant 3.41. You will get this value. And for appliance, you have to take from electrical department. Otherwise, you can take from design data book. It is coming 200. This also constant. This ballistic factor for appliance. This conversion factor. This also constant. So we'll get these values. So I will show you this appliance how we have to take from design book. Okay. This is the heat gain from office. So one second. Our office we are using computer monitors and printer fax machine. So here the watt is mentioned 55. This laser printer 130 watts, fax machine 50. So you can take approximately 200. Actually, we'll get from electrical department. Otherwise, you can take for office 200 watt. See appliance side 200. These values are constant. So you will get these values. So total room sensible you will get 8847.6835, and we have to add safety factor, so you will get 84.76. So total effective sensibilities, if you add these two values, you will get 9732.45187. So effective room sensibilities 9732.45187. Okay. Now latent heat. Here people, our office 3 people are there, 3 people, and latent heat as per design data I have shown you before, it is 205. So you will get this value 650, and infiltration it is 13.33, and humidity ratio for infiltration is minus zero point 0.1 here. And this is conversion factor is 0.68, it is constant, so we'll get this value. And bypass outside air is this one 20.86. Humidity ratio is, difference of humidity ratio is -1. This conversion factor is constant 0.68. This bypass factor is, it is also constant 0.1. So if you multiply these values, you will get these values. So total room latent heat is 604.5144. Okay, and we have to add safety factor 42.31608. So effective room latent heat you will get, if we add these two values, 646.830, and effective room total heat is this one, effective room latent heat plus effective room sensible heat, you will get this value 10379.2823. Okay. Now outside air heat, we already know the sensible heat is 20.866 and temperature difference is 18.2. This constant, conversion factor 1.08, 1 minus ballistic factor, 1 minus bypass factor, you will get this value, so you will get this value. Latent heat, this one CFM, this humidity ratio difference is -1, conversion factor is 0.68, and 1 minus bypass factor is, you will get 0.09. So you will get these values. So total outside heat is 356.36928, and if we add safety factor, it is 17.81. So effective outside heat is, you will get, if you add this, you will get these values. Okay. So you will get grant total heat of 1075.47 and ton of refrigeration is 0.8961. Okay. So here appliance is 200 watts and this is the usage factor, it is constant 0.75 and this is the conversion factor, it is 3.4. So it will come automatically 511.5. So total room sensible heat is 8847.6835. So effective room sensible heat you will get 9732.45187. Okay. Now this is done. Now I will do for latent heat. Here people in our office, 3 people is there, it would take automatically, and as per design data book the heat gain from the people is latent heat gain from the people is 155. So you will get here this value, and infiltration this 13.33, and humidity ratio difference is here -1. This conversion factor 0.68, so you will get this value. This bypassed outside air 20.86. This is humidity ratio difference -1. This conversion factor 0.68, and this is bypass factor 0.1. So you will get this value. So total room latent heat is 454.5144, and effective room latent heat you will get 486.33, and effective room total heat you will get 1021.8.7823. You will get automatically after putting the value. Now I will do for outside air heat. It will come automatically, no need to change anything. No need to change anything here. Only you have to put the humidity ratio difference, that is -1, and this conversion factor it remains constant, and here this 1 minus bypass factor. So 1 minus bypass factor you will get 0.09, so you will get this value. So effective outside heat is 374.18, and grand total heat you will get 10592.97. So ton of refrigerant you will get 0.8827 ton. Now here effective sensible total heat equal to effective room sensible heat divided by effective room latent heat. So effective room sensible heat we got 9732.45. Okay, and effective room total heat you get we got 10218.72. So effective room latent heat is 10218.8 here. Effective room total heat is 1021.78. So divided by this you will get effective sensible heat factor, this is 0.95240. Okay. So this is done, effective sensible heat factor. Okay. Now we will do apparatus dew point ADP with the help of ESHF effective sensible heat factor. We will get ADP. Here ESHF we got 0.95. So with the help of this value we will check in design book. See, this is the apparatus dew points. Okay, see our these are the dry bulb temperatures. Okay, our dry bulb temperature is 75 and relative humidity is 50. Okay, in this row we will check for ESHF. Dry bulb temperature 75 and relative humidity 50. We will check ESHF in same row. So ESHF we got 0.95. So here 0.95 is not there. So we will go for higher value. 0.92 is there, 0.95 is not there. So I will go for higher value 1. For 1 ADP is 55.2. Okay. So I will put ADP as 55.2. So this is ADP, that is 55.2. Okay. So our final ton of refrigerator is 0.8827 tons. Okay. So this complete our heat load calculation. Thank you guys.